Hey guys, so it's been a long time since I've done a blockchain video, and I've been moving house and a lot of other sort of crazy stuff going on. So I'm going to pick it up from where we left off. If you remember, there was a video I shot in Sri Lanka. I'll link it down below. Please watch that before watching this, otherwise it's not going to make any sense unless you're already familiar with locking scripts. And also the idea of unspent transaction outputs, the UTXO. We used a couple of analogies with real money to sort of highlight the idea of the fact that if we have bitcoins, or indeed if we have cash in our pocket, that's always a result of having been the recipient of a previous transaction. And then the locking and unlocking scripts, that video in Sri Lanka was really an introduction into really the syntax and how a locking script and an unlocking script are run side by side in a stack-based execution, and the final value on the stack determines whether the unlocking script has successfully unlocked the locking script. Okay, so I really sort of left the last blockchain video on a kind of on a cliffhanger, which is, well, how. So we know we've got this stack-based locking scripts and unlocking scripts, and we know we have unspent transaction outputs that we know is how we spend Bitcoin into a new transaction. And the question is now, how do we use those unlocking scripts and locking scripts to actually make sure that only the correct recipient, or the only correct, let's say, owner of that unspent transaction output can actually spend that untransaction output into a new transaction. Okay, so that's what this video is going to be all about. Okay, so let's get going. Right, so here we are, and we have a scenario here which might look a little bit complicated at first glance, but I promise you it isn't. And what's going on here in this diagram, I'll just find a thing I can use to make notes with. So what's going on in this diagram is that we have three fellows over here: hop, skip, and jump, right? And what we're going to describe is a very simple scenario where some Bitcoin is being transferred from hop to skip in one payment or one transaction, and then being transferred from skip to jump in a second transaction, right? So just as though they were transferring money, these guys we're going to see the propagation of the unspent transaction output from one transaction to another. And I think, hopefully, if you're still a bit confused about how the unspent transaction output actually transfers, if you like, from user to user, or from address to address, this might be a bit of a light bulb moment, hopefully. Okay, I think we've seen what I'm going to focus on primarily is, so we know that each transaction has conceptually has inputs on the left and outputs on the right, and nothing else, right? So a Bitcoin transaction is a very lightweight, a few kilobytes, very lightweight digital document, right? Just like a text document, whatever. And it has inputs and it has outputs. Okay. Now I think, as we mentioned already, the inputs to a transaction are the references that the spender is using to previous transactions of which he was a recipient, right? So just like, and we've seen that in the previous video, right? We've seen the idea that transactions have, even coin transactions can be thought of as a inputs on the left saying this is how I received this money, and then outputs on the right, which is this is where the money's going, right? So hopefully that's clear so far. So we've got two transactions here. So transaction ID, we're going to call it ABC, right? Just any value. We're going to call it ABC. We could call it transaction 1 or whatever, or transaction 2, but let's call it ABC. And then we've got transaction DEF. So transaction ABC is effectively the transaction in which hop transfers Bitcoin to Skip, right? So Skip was the beneficiary of this particular transaction down here. And how do we know that? Well, because so we don't care about these inputs. This is where these inputs describe where Hop got the money from, or the Bitcoin from. But this is a whole transaction chain, and we have to start the chain somewhere. So we're ignoring this side for now, but we're going to see two sides of two connecting transactions in the chain, right? So Hop transfers an amount of Bitcoin, right? Let's say, quite a big transaction. Let's say 2 Bitcoin. Okay, so Hop is transferring 2 Bitcoin to the address. The address in this transaction points to the Bitcoin address belonging to Skip, right? And if you remember, so I've done a detailed video on Bitcoin addresses. A Bitcoin address is essentially a hash of the public key belonging to Skip, right? So Skip has a one or more private and public keys, right? And if you take the hash of the public key, then you get, and then you do some, sort of a double hash, that effectively gives you the Bitcoin address, and you have to encode it in a special. I've done a very detailed video on that. So Hop specifies the Bitcoin address pointing to Skip's Bitcoin address. He specifies the amount of Bitcoin he wants to pay to Skip, and then he specifies a locking script, right? And the locking script is one that I basically pointed to briefly in the end of the last video. It's op duplicate op hash 60 of the public key hash, right? Op equal verify op checksig. So I'm going to go through in detail in this video about the different steps of this script and how they actually verify that that this ensures that only Skip and only Skip can actually spend this Bitcoin, right? So that's how Skip comes to be in possession of 2, let's say of 2 Bitcoin, right? So we're going to jump forward to transaction DEF now and take you through step by step exactly what's going on in transaction DEF. So we're saying, so Skip has received some Bitcoin from Hop, right? It was 2 Bitcoins. So Skip now has to create his own transaction because he wants to pay 2 Bitcoins to Jump, right? So Hop, Skip, and Jump. Skip wants to pay 2 Bitcoins to Jump, right? Now, what he needs to do is to first of all create a transaction and fill out the inputs and the outputs, right? So the inputs is quite straightforward, right? So Skip, his wallet here, right? So Skip doesn't create the transaction manually. He got his wallet software on his phone or whatever. It will create a transaction, and it will look at his unspent transaction outputs, right? So all the transactions that Skip has been a recipient of. It could be this one, it could be this one as well, and it will say, right, okay. So if I need to pay Jump 2 Bitcoins, well, so Skip has been the recipient of transaction ABC. So what this transaction is going to do is it's going to list transaction ABC as an input, right? And then you see the index here. So this will be 0. So this black line here points to the index output position of the output that he's referring to in that previous transaction, right? So in transaction ABC, there were, let's say there were several outputs, right? When Hop was in that transaction, there were several outputs, but the output at position number 0 was the one where which paid 2 bitcoins to Skip. So Skip has to reference this particular output, right, by saying, well, so transaction ID is ABC, right, and the position, the output position is 0, right, index position 0. If it put 1 there, then that would actually reference this one, right? So we're looking at index position 0, right? So that's great. The question is, right? The question is, how do we actually, how does Skip tell the Bitcoin network for sure that he is eligible to spend the output of this transaction, right? And the answer is he puts he has to apply a script, an unlocking script, which unlocks the locking script from the previous transaction. I think I've sort of, and we've seen this in the previous video, but so this one is going to be more about how we use digital signatures to actually provide a proof that I am Skip and that I can spend this output, right? So we're going to come back to exactly what these values are, right? That Skip includes in the inputs. We're going to come back to that in a second. But what we're going to do for now is we're going to work out, fill out the rest of this transaction. Okay, so what we're going to do is I'm just going to fill in. So we have to specify the output. So Skip wants to pay jump, right? And what he's saying is, so the outputs for this transaction, on the output side, we have only one output for now. Let's keep it simple, right? There's only one output, so position 0, the address of the recipient of this transaction is jump's Bitcoin address, right? Which is, let's say, in Bread Wallet, right? So jump's Bitcoin address is the address, and the amount is, let's say, I don't know, like 1.7 Bitcoin or something like that. I'm not going to worry too much about the amounts in this video, by the way, and I'm not going to talk about transaction fees or anything else. I'm just keeping it simple in terms of transaction chains and inputs and outputs. So please don't. There'll probably be some incompletions around, the fact that there's no transaction fee applied, etc., etc. So apologies for that. But so the amount, let's say, is 1.7 bitcoins, and it's a position 0. The address is jump's Bitcoin address, and the locking script again is, as always. Well, not as always, but as in this particular type of transaction, which is a pay to public key hash transaction, which is effectively pay to someone's Bitcoin address. It's op duplicate, op hash 160, op equal verify, and op check signature, right? So at this point, Skip's Bread Wallet, right, has created this pay to public key hash transaction, right? And it's a document, like a digital document. It has the input listed, in this case only one input, and it has the outputs listed. I suppose it's worth mentioning, in this particular case, this transaction input was referring to 2 bitcoins, and Skip paid jump 1.7 bitcoins. And I said I wasn't going to talk about transaction fees. I changed my mind. So in this particular case, we have Skip is going to pay 1.7 bitcoins to jump, and he's listed one output, which is 1.7 bitcoins. That means implicitly, because there's no explicit transaction, no explicit change paid back. So implicitly, there's going to be a 0.3 Bitcoin transaction fee, right? Because Skip has essentially not paid any. Normally the Bread Wallet or the Bitcoin wallet software will take care of transaction fees. But okay, so we've got a simple transaction with one input and one output, right? Now, how does this now we get to the key point, right, of the video. And the key point of the video is how do these scripts work, and how do they validate when I publish this transaction? How does it validate that Skip is indeed entitled to spend this 2 bitcoins from this transaction, this previous transaction, right? Because this is the new transaction where he's spending 1.7 bitcoins to jump, presumably in exchange for something else, like a like a stereo or something like that, right? So so how does that work? So the next thing, I'm just going to fade this in, is signing the document, right? So I'm just going to fade, if you can see what I'm fading out and in, right? So I mentioned that on the input side, the unlocking script consists of 2 components. It is a signature, which is this one, and public key, which is this one, right? That's so in this type of transaction, which is pay to public key hash, then the unlocking script, which is part of the inputs, which says this is how I prove that I'm entitled to spend this output, consists of a signature and a public key. So we're now going to talk about what exactly that signature is, okay? And it's actually fairly straightforward, right? So what it is, the signature, right, is essentially a question of taking, I'm just going to remove some of this. So I've done a detailed video on digital signatures, so please watch that if you're not familiar with them. The basic concept is that you any owner of a public-private key pair can sign a document, as in they can publish a signature along with the document, which effectively validates the contents of that document exactly as they are per that signature, and shows that that signature must have been generated by the owner of that public-private key pair, right? So if that doesn't make sense, please go and watch the video on digital signatures. It goes into a lot of depth. In a nutshell, what happens is the transaction that Skip has just created, right, which is basically everything inside this pink outline here, right? Everything here, right? But not including the signature or the public key, but everything inside the pink box, right? That transaction is, as a document, is passed through SHA-256 hashing algorithm, okay? Twice, as always in Bitcoin, everything is generally hashed twice. It's then encrypted with Skip's private key, right? So Skip has a private key and a public key. Jump has a public key and a private key. The private key is known only to Skip and nobody else. The public key is used to derive the Bitcoin address. So the hash of this document is encrypted with Skip's private key, right? And that becomes what's called a signature, right? So that signature is provided in the unlocking script, right? And it's a signature of this transaction that we've just created, listing the inputs and the outputs, right? In addition, Skip also provides his own public key in the unlocking script, right? So effectively what happens is, and this transaction document is now what gets published to the Bitcoin network, right? So the Bitcoin network, all the nodes on the Bitcoin network now receive copies. Let's receive copies of this transaction with the scripts, with the signatures, public keys, with the inputs and outputs, right? And at that point, and we still haven't quite got to the nitty gritty, which is, well, how does this script here, How do these locking scripts and unlocking scripts validate that only Skip can have initiated this transaction and that he was indeed allowed to spend the output from transaction ABC? Okay. I hope that's kind of still reasonably clear, but if it's not, then I hope it'll become clear in a few minutes. So the next stage is to validate, right? To validate, so all the nodes on the network, they have to now validate this transaction, and then eventually the transaction is going to get mined into a block and become part of the blockchain. Every node in the Bitcoin network is going to see this transaction. It's going to be validated and in the blockchain for all time, right? But in order for that to happen, every node has to validate the transaction per the standard rules, and then relay it on until the Bitcoin miners eventually will pick it up and process it into a block, right? So the last stage, which is really the whole point of the video, is validation, right? How is this transaction actually validated? Okay, so we're getting to the business end of the video now, and I'm hoping all will become much clearer now. I'm going to fade in the last piece of the jigsaw, which is the validation, right? And it's really quite straightforward. So this diagram is starting to look, I guess, a little bit more complicated now, but hopefully I've built it up gradually so you understand what each of these squiggles mean. Now, so what we're saying is this transaction that Skip has created, right, and has basically propagated to the nodes on the Bitcoin network. And these nodes are now going to start validating this new transaction. Right? They're going to validate the transaction and decide, right, is this a valid transaction or not? Right? And the way they do that is to evaluate exactly the same question as I discussed in the previous video, where I talked about locking and unlocking scripts, in the sense that what they're going to do is they're going to put the unlocking script side by side with the locking script and execute them in this stack-based execution and see whether effectively the value true remains on the stack at the end. And if that is the case, then the transaction is considered valid. And if it's not the case, then it's not considered valid. And so in the previous video we showed a simple script where anybody providing an unlocking script, which could make the final that could solve the puzzle of how to, what number do you add to 1 to make 2. It's exactly the same here. It's just that the items in the locking script are more complicated, and that's what we're going into now. Okay, so we said the unlocking script was the signature of this new transaction signed with the private key belonging to Skip, the person who's spending the Bitcoin, along with his own public key, right? And then the locking script, which was specified in the previous transaction, which Skip is spending here, was op duplicate op hash 160 with Skip's Bitcoin address, right, which was the hash of Skip's public key, followed by op equal verify and OPCHECKSIG. And it's a question of really what does op equal, well, we know what op equal verify does, but it's really what does this OPCHECKSIG thing do in a nutshell, right? So here we go. Let's just step through one by one what the stack looks like at each point of the execution and how we achieve what we're trying to achieve here, right? So this is item number 1 in the stack. This is item number 2, 3, 4, 5, 6, 7. So the first 2 come from the unlocking script, right? Which is the signature, and the public key comes from up here. And then and then 3, 4, 5, 6, and 7 are all the terms from the locking script from the previous transaction ABC, right? So let's step by step, right? So at point number 1, so we just put the signature, which is this value here, we put that on the stack, right? That's pretty straightforward. And number 2 is just the public key, right? So it's just a value. When we see a value in the script-based execution, we just put that value on the stack. So at this point, the stack has signature on the bottom, and then the public key provided by Skip. This is Skip's public key. Remember, and that public key comes straight out of Skip's wallet, right up here. So we have the public key and the signature on the bottom, then the public key. So then we're moving on to number 3, right, which is this one here. We see op duplicate, right, which means take the top item on the stack, copy it, and put it on the stack, right? So now we have the signature and then 2 copies of the public key on the stack. That's pretty straightforward as well, right? Then so number 4, there's an op hash 160, and what op hash 160 does is it hashes the top item of the stack. So it removes the top item from the stack, hashes it, and then puts the hash back on the stack. So now we have, instead of the public key on the stack, we have 1 copy of the public key, but then we have the public key hash on top of the stack, right? Which is pretty straightforward, right? So number 5 is where it gets interesting. So we said take the public key hash, this from the locking script, which is this one here, right? This is the public key hash, is basically the Bitcoin address of ABC, was the value that of the intended recipient of this transaction. So that is the value that we put on top of the stack here, right? This is from the locking script of the previous transaction. So now we have Skip's public key hash, right? Then we have the public key hash from the previous transaction output from the locking script, right? And that's what the stack looks like. Then number 6 says op equal verify, which basically says take the top items from the stack, the top 2 items from the stack, and if they're equal, right, then just remove both of them. Okay, so if, as long as these 2 items here are the same, then they're both going to get removed from the top of the stack, right? They're going to get removed. Now it's worth thinking about, I'm sorry if I'm repeating myself a little bit, but it's worth thinking about the significance of this step, because what we're saying is, in this transaction here, right? In this transaction here, Hop was saying, I'm paying 2 Bitcoins to whoever has a public key that has this particular hash, right? That's what the Bitcoin address is. So that was in the locking script, and let's call that public key hash. Let's call it public key hash dash, right? So I'm just going to put a dash there. This is the address that Hop specified should be the recipient of these 2 Bitcoins, right? So if we go down to here, this one here is the Bitcoin address hash, right? As is this one. This one here, the public key hash, is the hash of the public key which Skip specified in his unlocking script, right? So what they're basically saying is, simply put, right, has Skip in this unlocking script has skip provided a public key whose hash is this, right? That's basically what's going on there, right? If skip has not provided a public key whose hash is this, then this op equal verify is not going to remove these two from the stack, and as you'll see, we're not going to end up with true at the end of the stack, at the end of the execution, which means that the transaction is not going to be valid. Okay. And then the last one is perhaps the most important, right? Which is, so we've got the copy of the public key from the very beginning. We've still got that on the stack, right? So we've still got the public key on the stack from all the way through. So we've still got one copy of the public key specified by skip in the unlocking script. We still got that, right? So what do we do at this point, right? Well, so it's actually fairly straightforward. We have two items on the stack. We have the signature, which is this one, and we have the public key, right? So the original values, we have them on the stack, and we apply a OPCHECKSIG to these two values, right? OPCHECKSIG, which is check signature, and see whether true ends up on the stack. If any other value than true ends up on the stack, then this transaction is going to be invalid, and all these nodes are basically going to refuse to accept it and relay it on. So that transaction is never going to make it into the blockchain, which means that this payment, right, this payment of 1.7 bitcoins to Jump is never going to happen. It's never going to be recorded, and Jump will never receive that bitcoin and never be able to spend it, right? So really the last piece of the jigsaw is what on earth is this OPCHECKSIG operation here, right? What does it do? Well, it's quite simple, right? So we have a public key, right? And we have a signature. So all we do is we say, take the signature, right? Let's go for a darker color. Take the signature, and we're going to decrypt it, right, with the public key. So decrypt. And the output of this is going to be a hash, right? That's how signatures work, because the signature itself, if you remember, was created by encrypting a hash. So we took the original transaction up here, we hashed it twice, right? And then we encrypted it with the private key. We encrypted it with, so if you remember, Skip encrypted, when he created the signature, he encrypted this hash with his own private key, right? This one here, right? The public key is used in the actual unlocking script. So that's the public key we're using, right? So you can see the importance of the public-private key pair, right? So just go down again. So effectively, what happens here is that what's happening here is effectively this, but just in reverse. Okay, so we take the public key from the unlocking script, right? That's this one. We take the signature, right, which is this one, and then we decrypt the signature using the public key, right? And that gives you the hash, right? And that should be this value, right? so these values should be the same. Okay, so at that point, it's very easy to say, well, okay, so all I have to do now is check that the hash of the actual transaction document, right? Put this through SHA-256, and then again. And see, are these equal? And if they are, then the signature is valid. Then the signature is a valid signature for this transaction. At which point, OPCHECKSIG is going to return the value true, and it's going to remove public key and signature from the stack and replace with the value true. And that's the only way that the Bitcoin nodes will validate this as a successful transaction, right? So that's it in a nutshell. It's so essentially, if you think about what's happening here, Skip has a public key, okay, which he uses to derive his Bitcoin address. He has a private key, which is associated with that public key, which he uses to sign transactions which spend outputs addressed to his Bitcoin address, right? So you can say, I mean, the relationship between the public key, private key, and Bitcoin address is hopefully clear now. It's the fact that only Skip has access to this private key that can create a signature for this document, okay, which is signed with this public-private key combination. And that public key is also, the hash of that is the Bitcoin address, which enables Skip to have that Bitcoin in his possession in the first place. So if you've got any questions on that, just give me a shout. It's probably the most complicated video I've done on this stuff, but it's also potentially the most important. So I kind of feel that if you understand this, I want to show you sort of a complete, let's say, complete transaction chain, and show you how the Bitcoin is transferred using these signatures and using these public-private key pairs, and really sort of make the relationship very clear between the Bitcoin address, the private key, and the public key. And I think just before we, sorry, I've switched, the DSLR ran out of batteries, so I just switched back onto the Mac mic. I think it's worth sort of considering. I've kind of talked through the success scenario, right? The success scenario here is that Skip managed to spend a Bitcoin output that was bound to this address, which was the hash of his own public key. He was able to spend that because he was able to provide a signature and a public key which satisfy all the conditions in this script, such that true is the value that ends up at the end. But just to hammer home the point, what if, let's say, what if Jump instead, right, had just said, do you know what, I'm going to look at this transaction here, right, that's addressed to this particular Bitcoin address, and I'm going to try and spend this transaction output, right? What happens? Let's say Jump is a guy of dubious scruples, right? And he wants to. So what's stopping Jump from actually spending this transaction output? What's stopping him from doing that? So Jump could also provide Jump has his own private key, right, and his own public key, right? So what Jump could do is also he could create a very similar transaction to this one, right, which refers to this this transaction ABC, output 0, right? And he could, create transaction outputs and try and spend it to Bob or whoever he owed Bitcoin to, and say, right, there you go, there's a transaction. He could sign it. He could sign that new transaction with his own private key to create a signature and provide a signature, right? And provide his own public key instead of Skip's, right? Or he could provide Skip's public key but provide his own signature, because he doesn't have Skip's private key in order to create a signature that is valid per the rules of the OPCHECKSIG, right? So let's say Jump, for example, so there's two scenarios, right? First of all, Jump provides his own public key and then provides a signature based on his own private key, right? So at that point, if you think about what's going to happen in the stack, so Jump's signature is going to be there, right? His evil signature. Jump's public key is going to be there, right? Then Jump's public key is going to be duplicated. Then Jump's public key is going to be hashed, right? And then, but the locking script, so now the locking script, the actual Bitcoin address of the locking script is going to be put on the stack. And when op equal, which is op equal verify, when that runs, these two are not going to be the same, right? Because the hash of Bob's public key is not this address, right? So that at that point, the game's over. This attempt of Jump to spend this transaction output is dead in the water. So what's the other thing we said Jump could do? Jump could he could try and basically put Bob's public key, right, in the unlocking script, right? Jump could do that. And he could then sign the transaction with his own private key, right? Because he doesn't have Skip's private key, but he has his own. So he can sign that transaction with his own private key. So what's going to happen then? Well, so the signature that Jump provides with his own private key is going to be on the stack. Then we said that. So Jump provided Skip's public key, which is the correct public key, so that goes on the stack. Then that gets duplicated. Then it gets hashed. Then the op equal verify is going to come along, and in this case, yes, perfectly fine. Jump included the correct public key in the unlocking script to match the correct Bitcoin address that Hop had intended, right? So this one is going to actually be fine. Op equal verify will work perfectly fine. So then what we have left on the stack is Skip's public key and the signature. But at this point, if we remember what happens down here in the OPCHECKSIG, we have this is Skip's public key, right? And then the signature provided by Jump using Jump's private key, right? So if we decrypt this signature, right, with Skip's public key, right, and check and look at the hash, okay, that hash is not going to be the same, right, as the hash of the document, because in actual fact, the signature was created using Jump's private key, and therefore that signature cannot be validated using Skip's public key, right? So that hash there, that is not going to be the signature is not going to tie out, right? Because it was not signed by the private key corresponding to the public key, which for the intended address, right? So hopefully that sort of illustrates how it's really not. So Bitcoin transactions are not tied to individuals, right? This type of transaction is a pay to public key hash, and it's literally that. It's not okay. hop is paying skip. It's actually hop is locking this transaction output to whoever can provide a signature, right? Which effectively means whoever owns the private key corresponding, or whoever knows. I mean, let's not talk about ownership. Let's say whoever knows the private key, whose public key hash is this Bitcoin address, and that's it. So if 10 people know this private key, then 10 people can spend this transaction output. If 1 million people know about it, then it's basically whoever gets there first will spend the transaction output, right? So that's really how transaction outputs are tied or locked to the owners of private keys, and private keys correspond to public keys, correspond to public key hashes, which is Bitcoin addresses, and this is how the transaction, this is how the script, the validation script, runs and checks that before those transactions are propagated on the network. This is how it verifies that the person who is spending this transaction really does own the private key, or really does know the private key and has used the private key to sign the document, right? So hopefully that has been useful. This is one of the messiest diagrams I've ever written, but please leave any questions if you do, because it's a very important topic. It's kind of, I think once you get this, you kind of should finally, I guess, have that sort of penny drop moment where it kind of all makes sense. If it doesn't, then let me know and I'll answer any questions. If you like the video, please give a thumbs up and subscribe and all that. I'm actually going to start doing some videos on Ethereum very soon, and then I'll probably come back to Bitcoin at some point. But thank you very much for watching, and I'll see you in the next video. Bye.